Okay, friends, today is Saturday and the time is 8:30 p.m. in Indian, that standard time. So good evening to everybody and to the people who are residing in this part of the globe, and good afternoon and good morning to the rest of the people as they belong to. So we are here for the Saturday manufacturing talks. As you know that the Saturday Manufacturing Talks, we are organizing our Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. We are organizing this webinar series, mega webinar series, since March 2021. So today is the 45th week. Each Saturday, we are fortunate to have the eminent speakers from the different parts of the globe speaking about their thoughts, their experience, their research expertise in the fields of manufacturing. So it's a very good, the platform so far we are all enjoying and having a lot of interactions and all. And specifically for the Center of Excellence, as you know, the Center of Excellence is industry focused, the research, the center at IIT Kharagpur. We do have quite a few the industries with us, public sector industries, and then the private sector industries are there. We are solving problems for their the industries. So having this webinar series, listening to the eminent speakers from the different parts of the globe, we are also getting our own knowledge enriched. So this is a very good the experience that we are all having, and we are fortunate to have today with us Professor Fengshou from the University of Huddersfield in the UK. Professor Fengshou is a professor in diagnostics engineering, working as the head of measurement and data analytics research group, and the deputy director of the Center of Efficiency and Performance Engineering at the University of Huddersfield. He had his BSc and MSc from Taiwan University of Technology, China, and PhD from University of Manchester in the UK. His research interests include machine dynamics, tribology, dynamics, advanced signal processing, measurement systems, and sensor development, artificial intelligence, and also condition monitoring and diagnostics. So you can see that the vast experience, and this experience is very much needed, for doing research in the field of Industry 4.0. Today we all know that we are standing in the era of Industry 4.0, which is a vast, the area having different, the modules, and it is very difficult to get a person having expertise in the different modules like the signal processing, image processing, condition monitoring, artificial intelligence, machine learning, and all. So we are fortunate to have Professor Gu today with us. Professor Gu is working in the field of condition monitoring and diagnostics for more than 30 years in developing advanced monitoring and diagnostics techniques, laboratories and numerical simulation methods, and published over 300 technical and professional publications in machine modeling, fault diagnosis, signal processing, measurement systems, and related field. He has undertaken a number of research programs of marine powertrains, turbine machines, electric motors, internal combustion engines, reciprocating compressors, centrifugal pumps, hydraulic power systems, gearboxes, and bearings. He has experience in system modeling, various physical parameter measurements, advanced signal processing techniques, including time frequency analysis, wavelet analysis, adaptive signal decompositions, artificial intelligence algorithms, and statistical analysis. Recent research interests are on energy harvesting, instantaneous electrical signal analysis, tribodynamics, airborne acoustics, remote measurements, wireless sensor networks, and online model identification for promoting system efficiency and reliability by accurate, the machinery monitoring. He has supervised 30 PhD students undertaking a number of projects funded by UK and Chinese governments and industries. So with this, the brief biosketch of Professor Fengshou, let us, listen to him on a topic, monitoring turning processes and diagnostics. And we all know that the essence, the crux of the industry 4.0 today, the data, and the data has to be generated and it has to be analyzed through signal processing. So let us listen to it. Professor Gu.
Thank you, Professor Paul. Thank you for your introduction. So I'm very pleased we have such a great opportunity to join your webinar to share our experiences, to learning also from you when you give us some comments, advice about the work we have done. Right. Firstly, I would like to just introduce a little bit our team today. Let me see screen. I'm not quite sure. Is okay?
Yeah, it has come up. You can
right.
go to. Yeah.
Basically, as you see,
Excellent.
the subjects or topics that we are going to talk about monitoring machining process. We particularly called ORS, OIES, on-rotor sensing technologies and instantaneous electrical signature analysis. We choose this subject simply because that many people doing high level intelligence, unfortunately, sometimes we realize the data quality is not so good. So we think we're supposed to solve the problem from the ground, get good quality of data first before we're doing something further. So based on this one, we will have two presentations, one from Trini, my colleague, and another one from Jason Ju, my colleague. They are each focused on different subnets. For example, first one for the ORS, second one for IES. I supposed to do this one myself today. Unfortunately, I have bad cold. I keep coughing, so I just worry about the quality I can present. So I invite two of them to present the work first. So then what I expect is that when we can have a good time for discussion, either in middle that the first one finishes the presentation, or we can do it at the end of the presentation, whatever we think is suitable. So basically, we call T-Pen. We also have a kind of network we call the efficiency performance networking. 29 based on all our research team in UK CPE. But as you know, like your platform is we have some restriction from university wide. So therefore, we set up TP network so that we can assist network members to achieve their personal and the institutional objective. Right. That the network we have, I think probably some of you already be on our network website. Right. So most of at the beginning is from China, UK. As you can see, now the activity that we, as you see, we have a new journal launched in 2022. We will organize our third, I think, first conference, TPIN conference, to 22. You can have a look some facility we have right on site. Okay. So virtually, basically, did I already stopped it, right? So I already stopped my sharing, right?
Yeah, you have come out of your the screen. So you please share once again.
I think that what I would like to talk to start with. Then I'll hand over to the first presenter, Chen. Can you present the work you have done?
No, I can't share my screen.
Yeah, Ananta, can you give access?
Yes, I can share.
Yeah.
Yes. Okay.
Yeah.
Okay, shall I begin?
Yeah, sure. Please.
Okay, thank you. I'm Chen Li. I'm from China. Today, my topic is about machining condition monitoring based on vibration data from on-rotor sensing. I will introduce my content in 5 parts. Firstly is the introduction. As we know that the machining is very important in our manufacturing, and it reports 17 to 80% of the parts are formed by cutting, and they such as the turning, face cutting, trimming, and milling, and so on. With the development of technology, so there are more intelligent machines such as the CNCs, and almost all the processing could be conducted in the intelligent machines. But as for the condition monitoring, it's very difficult due to 3 factors such as very complex machining process, various impacting factors, and it's very difficult to install the sensors. This figure shows that the geometric errors in the products, and these figures show the changes on this face of the products. And this is show the tool wear or tool broken. So it's very important to do the condition monitoring during the machining process. As for the machining condition monitoring methods and sensors, for the methods, it is reported that there are many different methods. Firstly, and the main methods is about the stability analytic method, and the second is about the signal-based monitoring. And for the stability analytic method, it's mainly about such we do some research about the parameter side. And when we do the machining process or the cutting, we just need to check the stability parameter side and do as in the stable parts. But we also know that even though we do as the such as the 2 or the least parameters, stability parameters, but some uncertain such as the temperature or the tool wear will happens. So will reduce unpredictable results. In this view, we can see that the signal-based monitoring is also very important. So for this report, we just focus on the signal-based monitoring. As for this method, we can see that the vibration signals occurs the main path more than 10%. So as for my report, I focus on vibration signals. When we need to obtain the vibration signals, we need the accelerometer sensor. As for the traditional way to obtain or to fix the accelerometer sensors on this knees or for the machine, and this figure shows that the example of how to fix the sensor on this laser turning leads. The 6 is about the accelerometer in the field direction, and the 7 is the accelerometer in the current direction, and the 8 is the dynamometer. And we can see that these sensors need light to transmit signals or to obtain the power support. And we know that due to the light of the sensor, so they have to fix on this stable or stable leads or some tool holder. But when we needed to monitoring the quality of the workpiece, such as this vibration signals is direct, indirect. So we just think maybe we can obtain or fix our sensor on this workpiece, but
Hello.
Hello, I think he is outline.
Yeah.
Drop the line.
Yeah.
Just
Can I-
waiting for a second.
Can you hear us, Lee?
Just waiting for a moment. She is reconnecting.
Yeah. No issue. So what's the time now in China right now in Lee's place?
China.
hello, can you hear me?
Hello. Yeah. You can start. Yeah.
Okay,
You can
sorry.
continue. You can continue. You can once again share your slide.
Okay. Can I see
Don't
my
worry.
screen?
Don't worry. It happens like that. Don't worry. Please go ahead.
Yes, it's the poor Wi-Fi. So yeah, okay. So that the colleagues in our research center developed the on-road sensing. We call it ORS. To obtain the vibration signals. As for this ORS, we designed the hard device and the intelligent app. For the hard device, it includes accelerometer, processor, and the Blue or Wi-Fi module. Also, the power supply. This figure shows the path of the ORS. And when we doing the training experiment, we put this path in the sensor box. So and mount it on the end of the workpiece. Then when we do the experiments, we use the OIS to get the vibration signals. And this is our first version of the sensor box, and the frequency range is 1900 Hertz, and the dynamic range is 16 G. When we do the experiments, we find that the dynamic characteristics of the spider rotor have a big impact on the vibration signals. So firstly, we established the finite element model of the spider rotors. This is our model. And from this model, we can see that these spider rotors are mainly supported by two set of bearings, the rear bearings and the front bearings. And I simplify the rear bearings like this, the radial spring support, and then I simplify the front bearings using the radial and axial spring support. Then we can write the simple equation like this one, and the F is the periodical total cutting force. The Kc is the coefficient related to the workpiece material, heat treatment, cutting angles, and depth of cut. And F sigma is the stochastic cutting force. The stochastic cutting force can be written like this one. And the big T represents the Gauss distributed white noise, and the delta, mu, and sigma are the mathematical parameters specific to the parameter site, and the delta related to the cutting velocity, and mu is the chip-wise edge, sigma is the ring angle. So we just rewrite the equation like this one, and we can see from this equation that this part related to the true wear conditions and depth of cut. And this equation, this part, we can see that this stochastic cutting force can induce resonance. Based on this, and this is the mass of the system. So take these three factors into consideration. Firstly, we take the mass of the workpiece into consideration. We set 4 different mass, mass 1 to mass 4, and their mass quality increase, and they have different diameter and lengths. So we firstly use the FEM model to obtain the natural frequency, and we can obtain different models. Because of the frequency of the ORS, frequency band of the ORS, we just focus on the frequency below 1,000. And this is the model 3. And we can see that this is about the front end transverse vibration. And the mass of the workpiece have a big influence on this vibration natural frequency. And this is the back end, also the belt end of the spider. It is the 4th or 5th back end transverse vibration. The mass of the workpiece have little influence on it. And the 6th is the longitude vibration, and the 7th is the total vibration model. To verify the FEM results, we did the impact hammer test. We can get their results, FRF results, and we can see from this result that with the decrease of the mass, we can, even though they have a different mass, we can also can obtain their front end transverse vibration, and they increase with the decrease of the mass of the workpiece. Also, we can obtain the longitude vibration is about 700 Hertz, and this total vibration is about 1,000 Hertz. Based on this analysis result, when we doing the experiment, we set 3 different DOC. 0.1, 0.5, 1.0, and 1.5. And also we have two different clamping ways, the fixed spring clamping ways and the fixed pinned clamping ways. Both these two clamping ways, we can simply see there are two resonance frequency bands, and they are constant with the impact test and the FEM results. Also from this figure results, we can see that the greater of the DOC, such as the red represents the DOC is 1.5, and the blue one represents 0.5. So later on, we just use the two different frequency band filter to get the filter data, and we just calculate the RMS of the different after the two bands filter and get the result. We can see that the different DOC can be effectively separated, and also the fixed pinned clamping ways is more stable. As for the second experiment is about the two-wear condition identification. There are three different two-wear conditions. This one we call breaking two, and steady wear two, and failure two. Also, we need I use the on-rotor sensor to get the vibration signals. We can this is our raw time domain signals, this frequency domain signals, and we can see that this is the signal about failure two. We can simply see from this time domain signals that the area of the two-wear, the higher of the vibration amplitude. Then we use the same method and calculate their MS, and also we can separate or identify the different two conditions. And we also know that with the decrease of the mass, the natural frequency of three model increase. So for the second method, I just calculate the spectral center, and also we can get a good result. Finally, is about the experiment we conducted on the CNC leads recently. This is our tool insert, and we milling the workpiece until the tool insert failure. And these some figures about different tool stations. And with the time, and this is our second version of the sensor box, and it is obtained on the two holder, and is rotating with the spider. With the same method, we also could get some results. Okay, finally, it's about some challenges. Maybe challenges when I did the experiments. Firstly, it's about the various parameters affect the machining process and the characteristics of the vibration data. Second is about nonlinear and unstable relationship between the cutting parameters and the signal course. It is very difficult to establish an accurate model. Finally, is the inhomogeneity of workpiece materials and the nonlinearity of the system parameters, resulting in uncontrollable and unpredictable results. Okay, that's all.
Okay, thank you, Chenny, for presenting your works to everybody. Sajja, do you like make some general discussions with this work? Is anybody? Then we go to next one.
What I would suggest is that you you can go ahead with your presentation first, and then at the end we can have the discussions.
Okay, that's good. So, Jason, you present yours first.
Okay. I can't share my screen.
So we'll give you the access. Ananta, could you please give her the access?
Yes, sir. It is given.
Thank you. Yes, can you see my screen?
Yes, come in.
Yeah, you can go to the
Okay.
presentation mode. Yeah, that's right. Yeah, brilliant. Please go ahead.
Okay, thank you. Hi, everyone. My name is Zhe Jiangzhou, and my report today is instantaneous electrical signal analysis for online monitoring of machining operations. This is my report outline. It's divided into 5 parts. The first one is introduction and motivation. The term machining describes a variety of material removal processes, include turning, milling, and drilling. A cutting tool removes unwanted material from workpiece in the form of chip to produce a desired shape. The machining operation monitoring tasks include detecting, cutting, and machine tools condition, check and maintain machine process stability, avoid machining to damage, and maintain machining tolerance. As shown in the figure, many objects can be monitoring. Workpiece and the tool are the main factors to ensure the optimum performance of complete system. Sensors are needed for in-process monitoring and feedback from controllers. According to the different sensor, monitoring method can divide into indirect measurement, direct measurement. Compared to other tools, motor current signals, MCSA use the actual motor as a sensor to detect problem in the system. It is not intrusive and co-infective, so it is widely accepted as a valuable tool. In the literature survived, it is not clearly that is a clearly mapping relationship between the current signals and machining parameters to wire process and surface quality. So you can see this is a framework of research processing. As a result of the no line coupling of the system, we had to describe and quantity the uncertain in monitoring signal. Moreover, I need to consider the impact of degree performance in the motor sensor system. So I must develop more effective signal analysis method to deal with weak fault signal and strong background noise. So my main research content are to develop an accurate physical model and advanced data analysis technique so that we can identify too well machining health condition and the workpiece quality. As we know, when a material is removed, cutting force is produced between the cutting tools and the workpiece. But changes in operated conditions are not reflected in static cutting force. So, if there are material problems present in load, torque and speed oscillation will occur and lead to additional frequency in the spectrum. A good way to obtain machining information is to examine the relevant frequency setbands. We know the signal analysis is include time domain, frequency domain, time frequency domain, statistical domain, For example, the wavelet transform and its derivation are widely used to process signal from picture extraction to reflect the two-phase machining vibrations. But those methods do not accounting for the modulation characteristic of the system signals. So I chose the MSB. MSB, the modulation signal by spectrum, significantly enhanced complicated modulation companions. The theory and experiments have shown that MSB analysis can produce outstanding results in detecting and diagnosing early fault of rotation machine. Although the extensive applications are in different fields, no report on MSB are used in machining state monitoring and fault diagnosis. You can see this is MSB algorithm flow is shown in this figure. It can be defined in the frequency domain like this. It shows that MSB produce at least two fixture value, magnitude and the phase, so it can be provide more diagnostic informations. To verify the effectiveness of MSB applied to motor current signal from the processing, I do a numerical simulation analysis will carry out use an AC motor model developed based on the lathe model. By applying multiple harmonic to Q to the electrical equation, the amplitude and the phase, this is magnitude and this is the phase of the modulation sideband are extracted according to the preview formulate and present. You can see this. It shows that the phase is more sensitive to change in both static load and dynamic oscillation that appearing in typical machining processing. And for the case of the BRB, brake rotor broken and the electricity motor shaft electricity problem, both phase and amplitude show significantly change. So it also can be used to detect BRB and electricity problem. So we performed experiments based on turning shaft-like workpiece on a universal lathe to verify the analysis. The figures show that the power transmission system of the lathe, which is powered by a three-phase induction motor, an accurate clamp measures the motor current. We use a different DOC or adapt to study the difference. You can see this is the character frequency of this system. You can this figure compare two signal of the same turning workpiece with two different depths of cut. We found it make difficult to decide which is which. MSB magnitude result are most evident at the 50 Hz slice of the MSB. So this method reduced both abundant sidebands and rhythm noise significantly. You can find the rotation frequency and the motor shaft and the spindle and other you can see all you can see. Using state current information, the moving part of the transmission system can be evaluated. So we examined the
sorry to interrupt you. Zhejiang, can you move your cursor around so that people can follow you better? Can you show your cursor?
Cursor?
Yeah, mouse cursor.
Mouse.
Yeah, cursors. 你那个公标。
Okay. You can find the rotation frequency of each moving part along with its harmonic. In figure, the spindle, motor, and the shaft, lay shaft. You can see the MSB pinks. So we found using state current information, the moving part of the transmission system can be evaluated. So we examine the change. It is possible to monitor the turning processing. As shown in the figure, the monitoring results are based on MSB magnitude. MSB magnitude are high fracture and unable to make different across turning condition. This following figure show monitoring result based on MSB phase. The key frequency are all completely separated apart from the motor frequency. This result it is consistent with the simulation that the magnitude are less sensitive to variation in static load and dynamic oscillation. The phase are extremely sensitive to turning parameters such as depth of you can say such as depth of cut and the diameter of the workpiece. Consider that they represent the combined effect of dynamic loads. They are usually indicator of manufacture qualities. You can see in this figure, I built another experiment test system on CNC lathe in order to examine the effective of the MSB method for two-wire and monitoring machining parameters. During the processing, three tools with varied degree of wear, break-in wear, state wear, and tool failure are used, and we collected electrical signal analysis. During the rough machining, DOC equaled 1.0 mm. The phase are more sensitive to the change of machining parameters, which can be used to identify two different machining parameter change. Monitoring the fishing result is not ideal. The fishing result, for example, the depth of cut equaled 0.5 mm. So we should improve the algorithm going forward. So in conclusion, the MCSA is in fact a tool for monitoring machining operations. The magnitude and the phase are reliable indicator of the turning condition. In the future, we need developing robust and reliable machining monitoring feature by improving signal processing techniques. The second, consider the influence of the bell transmission diagnostic monitoring result. The second, the development of a recognized model will use deep learning network for enhanced monitoring effectiveness. That's all. Thank you for your suggestion and comments.
Thank you, Jie.
Okay, thank you.
Is there any other presentation from your side, Feng?
Thanks. That's all from us
Okay.
today.
So, since a lot of doctoral scholars are there in this platform, they were listening. So I'm pretty sure they will have some questions. But before I move on to them, I do have some, the queries. The Lee, you have worked on the vibration-based condition monitoring. It is a wonderful work that you have done. And you have rightly told that the vibration is one of the important sensors that can gather, the useful information out of the machining process. Now, you have mounted the accelerometer onto the tool post, and also one case you have shown the accelerometer is mounted onto the tool spindle. Now, the question is that when you are transmitting the data, I'm just asking you this question from the real time, the feedback purpose, control purpose. So when you are transmitting the data, how fast you are transmitting it to the cloud?
You mean how fast transmission the data?
Yeah. Transmission of the data. Yeah, that's right. From the sensors to the processing unit. Because you are processing the data either maybe the edge device or maybe the cloud. You are doing this, you are running the the signal processing over there on the data which is getting collected through the sensors.
I think I would better to clarify it, Sergio. The system developed in current situation is to be embedded in edge computing. It's not thinking directly upload this data to cloud yet.
Okay.
I think we're thinking that rather than feed this data, this large quantity data, actually, the data sampling rate is 3,200 kilohertz. 3
Okay.
channels of vibration, X, Y, that is a lot of data up to if you send to the clouds, right? What we are going to do is that we will process data locally and give some advice or information for online operators for automatic system to feedback to control their cutting parameters within the local area, not thinking upload to the clouds. I think strategically, this kind of data suppose not going to the clouds. Probably in the future, the key features that she developed, like bands, RMS values, spectrum, centroid, this kind of data, just go to the upload to the internet, or what they call, even though it's not suitable, maybe upload to fog. Do you know fog computing? In between clouds and the edge. So your workshop, you got fog computing, you can do that for the whole rows of machine lathes, they doing similar parts.
Good. So I do have another questions to Miss Joe regarding, because Joe, you have worked in the motor current signature analysis, which is very, very popular we find a lot of applications of motor current signature analysis in various fields of the manufacturing. But getting right correlation with the process parameter and the output is a real concern till today. Now you are the collecting the data through the current sensor. Are you engaging current sensor for all the 3 phases of the supply?
Try that, Zhexiang. He's asking you, is 3-phase currently used or just use 1 phase?
Currently used 1 phase.
Zhexiang, can you hear us?
Yeah.
So,
hello. Yeah, I can.
Sorry. I just used 1 phase.
Or just use 1 phase. Yeah.
Yes.
So what I would suggest is that in future it would be better if we can engage the current sensors for all the three phases.
Yes, we will
And-
try.
And instead of current, you can also look into the total power, the power sensors. You can put the power meters, so which will take into consideration of both current and the voltage. We did some analysis, in this particular area, the motor current signature analysis. We can also share our literature, which you have published previously. I'll share it to you, so that you can go through that, and if it is useful, you can make use of that for your consideration.
Okay, okay, thank you.
And another thing is that when you are collecting, capturing the current sensor data, are you capturing only for the spindle current, or the entire, or the main supply to the machine?
Sorry, can you repeat the question? We not catch you.
Yeah, because
Sorry.
in your machine, you'll have different activities. Spindle rotation is there. Your feed movement would be there. So, are you capturing the data from the spindle current consumption, or to the supply to the the entire machine?
We capture the current signal to the main motor.
Yeah. So, what I would suggest
The
is
spindle motor.
spindle motor. Yeah, that's okay,
Yeah.
because if you are collecting the total, the power consumption or the total current, then there would be some, the relation may not be that accurate. So if you only consume the spindle motor current consumption, then you can have a better correlation on that. Okay, so with this,
You're quite right. The motor current signals has been long used or investigated, not only in our manufacturing machining process, but others as well. We did motor, we did pumps, compressor, etc. Right. The progress she made is that not only magnitude of current, say for example your power,
yeah,
your spectral amplitude, but the phases interactions,
Yeah.
that's something more sensitive to small changes. That's what we are. I do appreciate what she has done.
and I think you have used the Tektronix current sensor. Is it the Tektronix?
Electronics, sorry.
Tektronix, the make of the current sensor?
Yes, the
Because from the
what's the maker is cannot think of.
okay,
Jason, can you think of what's the maker of the sensor? No?
we do have one questions at the
Fluke.
chat box.
Fluke.
Fluke.
Oh, Fluke.
Yes,
Yeah.
Fluke. Yes.
Yeah. So we do have one questions in the chat box at this moment. It has come from Pooja. So what deep learning methods have you identified for the prediction model? So I think you have not yet applied any deep learning methods. Joe, did you apply any deep learning methods as of now, or it is there in your future works?
Deep learning. Jason Joe, have you used any deep learning modeling?
I think
Right now I don't use the deep learning network.
okay. But you have got the plan to use it.
Yes, because there's something deep
Some use.
complicated system. So I will use the deep learning network. Yes.
So would you like to use would you like to extract the features and then apply the deep learning method, or would you like to apply the deep learning method onto the raw data that you are gathering through your Fluke, through your the vibration sensor or the current sensor? You want to do a feature analysis first?
Always do it.
Yeah. Okay.
Yes.
In general, what the strategy in the team is that you may realize Jason's methods is kind of, in terms of information point of view, is more a higher level or kind of supervision level.
Yeah.
So the motor current signal is generally is global, comprehensive, but is less sensitive to small changes. On the other hand, our ORS technology is extremely sensitive to small changes, but it cannot give overall information about whole system.
Yeah.
So that's what we do in two extreme sense, then merge them together. So how do we do that? Firstly, we will thinking develop a model of physics-based correlations, then think about deep learning. Right? I do appreciate that nowadays, last 2-3 years, people is very fancy to use deep learning models. However, from a scholar learning point of view, we still suggest people have a in-depth understanding the physics you are dealing with, then you go to deep learning. Deep learning is good, but it's kind of black box, not very knowledgeable to engineers to solve their kind of practical problem. It is so practical. I mean, giving practical explanations to what they found. So we generally, in my team, we generally put it as a secondary stages for their studies.
Yeah.
Well, I don't know, probably is right or not. So we can discuss this issue always.
Yeah. One more question has come up in the chat box. In ORS system, which model of controller is used? On the on-rotor sensing system, what is the controller of your CNC machine? That is one of the questions asked. So,
Trini, can you answer this question? Karen.
Which mode controller? Actually, we just used the intelligent app to get the information.
okay.
It's MCU NRFC. Jason, he showed you that. It's NR. I cannot remember the model.
Okay, fine. So
Yeah.
It's available.
no, that's
Yeah.
okay. That's okay.
Hmm.
One question is coming up. Yeah. So if you get to know the details, please forward that. But let us discuss, since the time is there, or 2-3 minutes more. So one, and there is no question in the chat box. So I'm just having one more question from my side. You are talking about the vibration sensor, the sensing of vibration during the machining and all. So how do you ensure that it is vibration coming, arising out of cutting process, or is it, let's say, from something else, like the floor vibrations, from the foundation vibrations and all? So how do you analyze that in your signal? Yeah,
Trini, can you follow his questions?
Lee, can
basically asking, how do you know the data you are dealing with is from the cutting process?
Yeah. So is it, this question is towards Lee? Lee, can you hear us?
Yeah, I can hear you.
Yeah.
So how do you mean, how do we know the data related to the cutting parameters?
Exactly.
Yes. Actually, many factors will affect the vibration data. So when we do the experiment, we just once time just keep one parameter change. We keep other parameters just the same.
what you can do is that before cutting, you can also do a dry run. That means without cutting, you can run the machine at different process parameters and you can see the level of vibration. So once you get that data, and then when the actual cutting would be done, at that time you can subtract the information which you have already gathered from the current situation, present situation.
Sorry, I didn't catch you.
No, actually, you have done wonderful work, and the topic is very, very interesting. It is all the time relevant and all, and the deep understanding of the signal processing is very much required. As I mentioned at the beginning, that we talk about Industry 4.0, we talk about the big data, we talk about the machine learning algorithms and everything, but at the the bottom level, the data which you are generating through sensing and all, the data has to be properly generated, and it has to be correlated with the process itself. I think there is no more questions, so let us one more question has come up. Is it possible to analyze the variation of RPM of a motor to get the vibration level of it as per torque slip characteristics? This is one question has come up.
Can you repeat the question, please?
The question is that is it possible to analyze the variation of RPM of a motor to get the vibration level of it as per torque slip characteristics?
Actually, I think yes, we can do that. But for my vibration signals, I used just to analyze the cutting parameters or the cutting process. And Zhexiang's method is to use the current signals from the motor to analyze the cutting process. We will not use the vibration signals to analyze the RPM of the motor. It's just a separate data we used. It is not use the vibration data to analyze the vibration of the RPM of the motor, I think.
Yeah. Okay, Lee, another question to you. In machining, whether 3-axis accelerometer is used to find amplitude in 3 directions or only in 1 direction? I think you have used 3 accelerometer. Am I right?
Yeah.
So you use 3 accelerometers in 3 different directions. How many number of accelerometer did you use, Lee?
How many directions? You mean?
Yeah, for 3 directions.
Yeah. Three directions. Yeah.
Yeah, X, Y, G. You have used 3. Yeah. So, Mr. Sahu, so the 3 accelerometers are used for that. So with this, let us the stop today's session, because it's already 9:33 in Indian Standard Time, and the topic, we all know that the topic is very, very interesting. We can go ahead in discussing for hours together and all, but somehow we have to make a stop. So thank you so much, Lee. Thank you so much, Joe, and thank you, Professor Gu, for this wonderful work done by you and your team members. And we look forward to have more and more discussions because it is very much aligned with our the research activities, and also the research activities of other scholars who are from the different institutes and all. So we'll keep on discussing with you and interacting with you, and let us build a good ecosystem and good team so that we can do something in this particular field. With this, I'd like to close today's session. So thank you, Professor Gu, and I request Ananta to let us know the speakers of the next few weeks.
Thank you, everybody, for your time, for your valuable comments.
Thank you, Professor. Yeah.
Thank you.
So for the coming week, on 22nd of January, Professor Dragos, ex-ante from the University of Nottingham, Professor Dragos would be talking about the time-dependent manufacturing process, why the inverse problems need to be solved. This is very, very interesting. And then next to that, on January 29th, Professor Swaminathan Gopaleswamy from Texas A&M in US. He would be talking about the health monitoring for cyber physical system. See, all the topics are very, very relevant in today's context.
Excellent. So somehow, can you send?
Yeah, the videos. Yeah. So the
Not video. I mean, this by a weekly basis before the seminar. Ask your team to send me the link. So
yeah, sure. So we'll do that one
every week.
Yeah. So today we have completed 45th week. So only a few more weeks to go to complete the 52nd, 52 weeks, because we thought of doing it for a year. It's a mega webinar series. And you can, if you have missed any video previously held the webinar, so you can get it through scanning this code.
Thank you.
And all the videos are uploaded in the YouTube. So thank you, Professor, once again for your presence. Thank you all the audience, and I look forward to your presence in the oncoming Saturdays. Thank you so much. Bye.
Thank you.